I don't have a Kindle, so I don't actually know what its communication capabilities are, and so I would have to say no.
Maybe not the older ones.
Yeah, and they can probably go to web pages, so yeah, so no. No electronic devices. Sorry, it just opens up a whole can of worms, okay? Open book, open notes. Yeah, so you can bring your notes. Anything paper is allowed. Old-fashioned. Okay. Yeah.
What chapters are going to be on the midterm? Is it going to be up to today?
No, today won't be included because the scheduling material, you won't have had a chance to do a problem set on it. So let's actually go to the class webpage. So if you look at the non-responsive web page, there we go. Yeah, so it's basically through this content of week 5, right? So chapters 1, 2, 3, 4, although we only covered a rather small part of 4, basically the timed automata part. And 8 and 9. 7 is background information that we're not really going to be asking you any direct questions on, but 8 and 9 are very much fair game. And there may be some questions that are pertinent to the lab content. Okay. Right. So if you look at the homework assignments, basically the pending homework which will be due after the midterm, is covering chapters 10 and 11. So we're not going to question you about 10 and 11 on the midterm. Okay, but everything before that will be on the midterm. Okay? Yeah.
Not for the midterm, but when we do the presentation, how long can you talk, or what is the time limit?
Nominally 5 minutes. We're not going to strictly enforce that. If you really need 7 minutes, that's okay. If you only need 1, that's okay too. All right? But aim for no more than 5 minutes. Tuesday, right. Okay, any questions from people who were here at the beginning of class and aren't going to repeat questions that were already asked and answered? Okay, then let's talk about so where we are in the book right now is chapter 10, okay, which, and we'll move very quickly into chapter 11, okay, so 10 and 11 basically, where we're looking at the structure of operating systems, microkernels, and scheduling issues, okay, and there's a reference here that can be useful if you're interested in pursuing this further. All right. So I talked a bit about got into this at the beginning, but the key idea is that I'm focusing on a core set of services that an operating system provides, but that you often need these kinds of services in embedded systems even if there is no operating system. Okay. So in the context where there is no operating system, people talk about having a microkernel, which is really just a set of core services that handle basically the managerial functions. They can be as simple as just having a bootloader. Okay, so when you've got a microprocessor, often what you have to worry about in an embedded system is what does it do when it gets reset. All right, and the reset is typically that's automatically what happens when you first power it up. Okay, the processor is going to reset, and what does it do? Well, it starts executing code at some location. Okay, that's what a reset will do. So what do you want to have at that location? Well, if it's a standalone board, you're going to need at least some small amount of read-only memory, some persistent memory, okay, that has a sequence of instructions for this thing to execute on reset. All right? One of the things that might happen in an embedded system is that that sequence of instructions will simply copy a bunch of other contents of read-only memory into some location in memory and then begin executing code at that location. Okay, that would be a typical thing. So that's called a bootloader, right? The small piece of code that goes to some source of program, gets the program, okay, puts it into program memory and starts executing there as a bootloader. Sometimes it'll not be reading it from read-only memory, but it'll rather the bootloader might just sit and listen for bytes to come in on the serial port, okay? And then it'll just take whatever bytes come in on the serial port, stick them in memory, and then start executing, okay? That would be one possible design of a bootloader as well, all right? So you can get a lot fancier than that, of course, and today we're going to talk a bit about getting a little bit fancier and providing the core services that an operating system provides, which involve supporting the multitasking mechanisms, the I/O mechanisms, which are also multitasking mechanisms. Okay, so creation and termination of threads, timing of thread activations, handling of synchronization between threads, and handling of I/O via interrupts. Okay, so the things we're not going to talk about are higher level functions that are provided by an operating system typically. And it's important, you know, if you're doing embedded system design, you sort of have to understand that you don't always have these. In fact, it's quite common in embedded systems to have a rather small subset of operating system functions. You may not have a file system. Okay, we take file systems for granted if you're used to programming, but a file system is, there's nothing about a microprocessor that provides a file system. Okay, a file system is a software abstraction that's put on top of the microprocessor by an operating system. All right, so the outline of a microkernel, what does it need to do? Well, typically it'll set up periodic timer interrupts. So it defines an interrupt service routine and says every 30 milliseconds I want this interrupt service routine to execute. So it writes to memory mapped registers to set up a timer to raise an interrupt request every 30 milliseconds. And so every 30 milliseconds this interrupt request will come in and you'll start executing this interrupt service routine. That interrupt service routine is what gives the operating system a chance to switch between tasks. Okay. It'll also need to create some default thread structure. It's important when you're designing embedded systems to keep in mind that the machine is never idle unless it's powered off or in sleep mode. And even if it's in sleep mode, it's not really idle because when you put it in sleep mode, you set it up to wake up at some point. So it's really just in a very slow mode. It'll execute instructions over a very long period of time, but it will execute the next instruction at some point when it's in sleep mode, okay? So you've got to set up something for it to execute. You don't want it ever to be executing just random locations in memory. That's not good. Okay, so a key part of this is a thread data structure. If you want to be able to execute multiple threads, you need each thread to have associated with it a data structure. In C, that would be a struct. In C++, it's a class definition. In Java, it's a class definition. Okay, and there's a bunch of data in this thread data structure. It includes a copy of the state of the machine the last time the thread was suspended. That includes, you know, the contents of the registers of the machine, including the program counter. So where is the thread actually supposed to execute its next instruction? You also have to keep track of what the status of the thread is. Why do you suppose you have to do this? Why should a thread data structure keep track of the fact that you're blocked that the thread is blocked trying to access a mutex? Yeah.
So two reasons. First, you might not want to execute the thread that's blocked.
So wait a minute, you said you might not want to execute the thread if it's still blocked? Is that what you said? Yeah. You're Ryan, right? Yeah.
Because you have context switch costs, which will be high.
Right.
And the second reason might be if you want to run some sort of deadlock detection algorithm.
You want to run some deadlock detection algorithm? That's another one. Yeah. There's a third one, which is that your microkernel may actually be executing because some other thread just released a mutex. Okay. In which case, you now know that that new thread becomes enabled. So you can look at the status of the existing threads, find all the ones that are blocked on that mutex, look at priorities if they have priorities, and if one of them has a higher priority than anything else that is currently enabled to run, then you would choose to run it. And because you have a record in the thread data structure that it was blocked on that mutex, you can tell immediately that it is a candidate now to be able to run. Yeah. So this is the reason that you need to keep this information in the data structure if you want to do this, make these scheduling decisions efficiently. You may also keep track of things like execution time estimates. Okay, so in particular, if you have threads that are defining finite chunks of computation, in some circumstances, you might have estimates of how long those take to execute, and you could use those as part of your scheduling decision. Those estimates are hard to come by, typically, but if you have them, they can be useful sometimes. All right, so let's look in a little more detail at how this works. So you've got this timer interrupt service routine. What it's going to do is it's going to start executing a chunk of operating system code, which will choose which thread to execute next. And then when this interrupt occurs, okay, the first thing you do in order to make this thread scheduling decision is you disable interrupts. Why do you do that? Yeah. So you can't interrupt the threads.
The thread switching process, because if you do that, then you produce states.
Right.
Things execute whenever you're halfway to saving a state, you interrupt.
Right. Are you Chris? Damn. What's your name? Raphael. Who's Chris? Not here. Okay. Does Chris look like you? I don't think so. Okay. I'm bad at this, but I do. I'll get it eventually. All right. So yeah. So one of the key things, of course, is look at this. You got this data structure. You have one of these data structures for each of the threads, right? There's a lot of information in these data structures. It's many bytes. If you make any changes to this data structure, you better do them atomically, right? If you make a partial change to this data structure, an interrupt kicks in and your thread dispatch routine again gets invoked, and now you allow it to look at a partially updated thread data structure, you can get some pretty nasty bugs from that, right? So yeah, so one of them is you have to protect this thread data structure, so you have to ensure that any updates to that are atomic. Similarly, if you're storing the state of the machine, which includes reading its register values and writing them to a memory location, if an interrupt occurs halfway through recording that state, you go and you do something, even if that interrupt service routine doesn't do very much and returns immediately, it will almost certainly have changed some of the values of the registers. So now if you resume recording the state of the machine, you've recorded an inconsistent state. You've recorded partially the state before the interrupt occurred and partially the state after the interrupt returned, which is not good, right?
Doesn't the interrupt actually save all the registers first?
It depends on the architecture. So this, you know, to really get under the hood, you sort of need to look at the spec for the machine that you're running. Sometimes it's built in to the interrupt controller in the architecture to store the state of the registers. Sometimes the interrupt controller is just a dumb thing that all it does is update your program counter and start executing. It's got to at least record the program counter, right? But it could, you know, so the minimum it's got to do is stick the program counter on the stack and then write to the program counter and start executing. But if you have an architecture like that latter one, then it's up to you, as the first thing you do when you enter your interrupt service routine is to store the registers. Now, one of the reasons, by the way, that in architectures they would do it that way is that if you have a real quick interrupt service routine that can just execute in 2 cycles and be done and return, you don't want to spend many cycles storing the state of the machine, right? What you'd rather do is just record the registers that you are going to use in your interrupt service routine, and then you know, you can then restore those at the end of your interrupt service routine, and you save a number of cycles. Could somebody send email to Danica and tell her to stop doing email? Sorry, kidding. It's always tempting. All right, so what was I talking about, Danica? No, it's okay, don't worry. I do it too. All right, so yeah, so the issue, I mean, sometimes an interrupt controller does a lot more for you, but if the interrupt controller does a lot more for you, that usually comes with a performance penalty also, because it means that you know, an interrupt takes a minimum of, you know, 35 cycles, right? Because it ends up storing a bunch of machine registers and then restoring those before returning. And then, so then the quickest interrupt you can do is 35 cycles, right? So a dumber interrupt controller does less for you, but allows you to write really quick interrupt service routines. Okay. All right. So to change threads, to switch threads, what you have to do is you've got to run some scheduling algorithm. So the scheduling algorithm just says, all right, I've got a bunch of threads that are enabled. Which one should I start executing, resume executing? Okay. And so the thing we're going to look at today is what's the basis for making that decision. Once you make that decision, it's pretty straightforward to resume executing. In fact, what you do is very simply, you mess with the stack. Okay. You could do it by just writing to the stack pointer register to change the stack pointer to someplace else. Now it's going to point to the stack of the thread that you want to resume executing, and then you just return from interrupts. Okay. Another way to do it would be to leave the stack where it is and you know, update the data on the stack. But that would be more expensive. That takes a lot more cycles. So usually what you do is you update the stack register to point to some new place. Okay? All right, so there's a big distinction in scheduling between non-preemptive scheduling and preemptive scheduling. So in non-preemptive scheduling, threads are all finite executions. So you start a thread, and then you execute it to completion, and only when it completes do you make a new thread scheduling decision. That's a pretty simple implementation now, because you don't actually need to deal with suspending a thread, so you don't actually need the thread data structures anymore, or I guess you need some information about what threads might be pending to execute, okay? But you need a lot less information in the thread data structures. So it's very cheap, okay? But it's also not very responsive. It means that you know, you really don't have any multitasking going on. So non-preemptive scheduling is used. In fact, it's often used in safety critical systems where they use a strictly round-robin kind of scheme of execution. So in avionics systems, for example, often an entire distributed system is triggered by a broadcast clock that tells every processor, you know, we're in this phase, do this. And processors write to shared buses only at predetermined time slots, and consequently they don't have any contention issues for accessing those resources. And you don't use interrupts at all. You poll your sensors. So every time, if you have a sensor input, well, then when it's the right time to read that sensor, you simply read the memory mapped register that has the latest value of the sensor reading, and you don't ever use interrupt service routines. So in many safety critical systems, people are kind of stuck doing that kind of design because it's very hard to get the level of confidence that they need using multitasking. But almost all systems have some form of multitasking. There are interrupts that are going to occur. There are going to be timed events that are triggered by timer interrupts and so on. And so there's some form of preemptive scheduling involved almost always. Okay, so today we're going to focus on the decision about which thread to schedule. So let's just launch right into it. So now the first thing is, let's assume that all threads have priorities. Now, where do you suppose these priorities come from? Yeah, Raphael.
They can be defined by the user, say the thing that takes care of.
Yeah, they could be determined by the user based on some sense of the importance, right, of the task. That would be one possibility. If you have a thread that's dealing with the brakes, maybe it's more important to apply brakes than it is to apply acceleration, right? That's a good example. What else? Where else could priorities come from? Yeah.
Could it be random, depending on the random, just choose the random one?
Yeah. So could you assign priorities randomly? Yeah, you could. Yeah. What else? What's your name? Apurva. Okay, that's a good observation. So the observation is that if you know how long threads are going to take to execute, you might actually want to give higher priority to things that execute quickly, simply because you can get stuff done. We do this in our daily scheduling. If you have a task that's really quick and easy, even if it's relatively unimportant, often you do that before the important stuff because it gives you a sense of accomplishment. Same one, okay, yeah.
How about the process that wasn't been processed, not the process, the thread that wasn't been processed recently, so the oldest process?
Yeah, right, so there might be a fairness criterion, which is that if you have a thread that hasn't gotten a chance to execute in a while, you might bump up its priority in order to be fair to it. Yeah. Right. So round robin would be another approach where you that's actually kind of similar, right? Round robin would be looking at giving highest priority to the thread that executed the furthest in the past. But round robin could actually be even stricter, which is where you assign specific time limits, and every 30 milliseconds you switch to a new thread. Right? That's typically what's used in desktop operating systems like Unix or Windows or Mac. Notice that several of these ideas actually require dynamically changing the priority of a thread. So it means, the thread, one possibility is, when you create a thread, you assign it a priority, and that priority never changes during the entire execution of the thread. It's a very different scheme if, as things are executing, the priorities of threads can change. And it's more expensive to implement something where the priorities can change, right? If the priorities of threads are determined when they're created, the implementation is a bit simpler. So that's a distinction that we need to worry about when it comes to implementing these things, and it has an effect on what your possibilities are. Pretty much all of the ideas that have come up so far have been, in a sense, pretty ad hoc, right? They're kind of intuitive notions. They're not notions of any that have any sense of optimality associated with them, or anything where you could prove formal properties about some assignment of priorities. Turns out that under certain very limited circumstances, you can derive a rigorous basis for assigning priorities to threads. It turns out to be the constraints that you need to impose in order to have such a rigorous basis are pretty draconian, okay? And a lot of realistic scenarios don't actually fit those constraints very well. And so what designers have a tendency to do, sadly, is they will use the principles that we're about to talk to as a guideline. They will prototype the system. They will test it on the bench. And if it doesn't work, they'll tweak priorities. Okay? They'll try changing priorities to see if it works. And the problem, of course, with that approach is that it could work on the bench, and the failures that could arise from the priority assignment that they have could be rare enough that they don't see them on the bench. They may only see them in the field. So that's the thing that you try to avoid by putting some thought into this. Okay, so the first of the sort of basic principles is called rate monotonic scheduling. And this was developed by Liu and Leyland in the early 1970s. Yeah?
So when you said that the priorities can change dynamically?
Right. So the question is, if the priorities change dynamically, does that mean that the scheduler is running concurrently? So I want to emphasize that what does it mean to be running concurrently, right? I mean, assuming you have a single core, right, that executes a single instruction stream, then there's no true concurrency there, right? The only way you get concurrency is by interrupts that kick in and give a new task an opportunity to run. Okay, so the thread scheduler, we're going to assume for the moment that that's the scenario that we're in, okay, because it is the most common scenario. The thread scheduler runs only when it is given an opportunity to run by an interrupt, okay, or by a procedure call. So in particular, if you have a thread that makes a call to your pthreads library to acquire a mutex, okay, normally that will cause the thread scheduler to run. Why? Well, because if you attempt to acquire a mutex, you may block, so obviously you want the thread scheduler to run at that point. You don't want to wait until the next timer interrupt for the thread scheduler to run, because the currently executing thread is stalled. And remember that the processor has to do something, right? So what does it mean to stall? The clock's still going. The program counter is still going to get incremented. The processor's got to do something. You got to assign some value to the program counter if you can't acquire this mutex. So a reasonable choice is make the program counter point to your thread scheduling algorithm and let that code run to decide what to do next, right? So this is, I mean, if anything, the key thing I want you guys to get out of this is get out of this notion, that this illusion that the computers we use every day create for us, that there's a bunch of stuff going on at once, okay? For the most part, there isn't. Okay, and it's things are happening only when they get a chance to happen. Okay, so yes, it does mean if you have dynamic priorities, the key thing is that the thread scheduler needs to get more opportunities to run. In particular, anything that could change the priority of a thread needs to involve the thread scheduler if you have dynamic priorities. Whereas if you have static priorities, that's not necessarily the case, right? The priorities don't change, so the thread scheduler doesn't have to run when certain things happen. Okay, so that's where the complexity comes in. Yeah.
So if we are choosing the priorities depending on how much time
Yeah, so the question is, how do we know if we're basing priorities based on some prediction of execution time, how do we know what that is? That's the topic of chapter 14 in the book. Execution time estimation is actually an extremely difficult thing to do.
They do that in practice, like do they use the prediction time?
Typically not at runtime. The algorithms to estimate prediction, to predict execution times are static analysis of programs, and so it's not typically something you do at runtime. What you can do is simply penalize tasks that are running a long time. You know, give them a lower priority simply because they're taking a long time to execute. Right? That's not an uncommon strategy. Yeah, Ryan.
So not to belabor the discussion, but so when talking about static program analysis and trying to find trying to
That's a really good question. So the question is, does the halting problem affect your ability to estimate execution time? So given an arbitrary chunk of C code and an architecture on which to execute it, the time that it takes to execute that C code is undecidable. Okay? What that means very specifically is that there's no algorithm that can give you an answer for any arbitrary C code. Okay? Now that doesn't mean that given a particular chunk of C code that I can't give you an execution time estimation, right? It's that there's no algorithm that'll do it for all chunks of C code. So in practice, what people do with execution time estimation is they use heuristics that will give you an answer most of the time and will tell you when they can't give you an answer. Okay? And the fact that they can't give you an answer doesn't necessarily mean that that chunk of C code doesn't halt. They can't give you a definitive answer about whether it'll halt or not in general. Okay? But they can say, well, the heuristics I'm using are not good enough. I can't tell how long this thing is going to execute. And that's always a possibility with execution time estimation. So that, of course, complicates your ability to do this at runtime, because it means that any algorithm you use to try to analyze the code of a thread to decide how long it's going to execute is trying to solve an undecidable problem, which basically means if you want to spend more time trying to solve that problem, you have a better chance of solving it, but you never have any assurance of solving it in a finite amount of time. Okay. Yeah, so execution time estimation is, so I often tell people that this concept, worst case execution time, which is always written like this, is really a fiction, okay? Even if someone tells you that this is the worst case execution time of this particular piece of C code on this particular architecture, what they can tell you is not for a family of implementations, right? But for actually a particular piece of hardware. So they can't. I can't tell you. This C program on x86 will take 55 cycles, right? Because x86 as an instruction set architecture allows many possibilities for implementation, right? You can get really fancy with the execution. And you could execute in fewer than 55 cycles or in more than 55 cycles and still be a perfectly correct implementation of x86. So, all I can tell you is this particular piece of C code on this particular piece of silicon embedded in this particular board with this particular amount of memory, this particular cache structure, and so on. And assuming that there are no other tasks running and that the state of the cache is known before the program starts executing, then I can tell you it'll execute in 55 cycles. Okay? I have to have all of those pieces of information to give a definitive answer, which is, of course, bogus. Software doesn't work that way. So anytime you're basing things on worst case execution time, it's a bit of a prayer. Okay? Unfortunately, you have to. You have to do it anyway. It's the reality, right? You need to know how long things are going to execute. So it's a bit of a problem in the technology. All right, so let's look at this Liu and Leyland result. This is a classic result, right? It's in fact it's really sort of in some sense a definitive milestone in the field of scheduling, right? Anyone who's studied scheduling, you just mention Liu and Leyland, they know exactly what you're talking about. Okay, so it says that if you have a set of tasks that are independent, okay, so these are independent tasks that execute periodically with periods T1 through Tn. So that means, you know, they're going to execute repeatedly, and you want them to execute at least once within each time period. Well, actually, I think exactly once within each time period, okay? And you know the worst case execution times, a fiction, but a fiction that everyone assumes, okay? And there's no mutual exclusion locks, no semaphores, no blocking I/O, another fiction, okay? Doesn't happen. And there's no precedence constraints, another fiction. You have fixed priorities, okay? You're not allowed to change the priorities. And you are allowed to preempt tasks. So if there's a task that's executing, you can interrupt it and start executing another task, okay? Then, and so what we mean by preemptive scheduling is that at any time, we will be executing the task with the highest priority if that task has not already completed its execution within its time window. Okay, is that a clear statement? So every task wants to execute once within a time window. So task Ti has a time window of Ti, and it wants to execute once within that time window. So it's going to execute at this point, okay? Whenever it gets a chance. The issue is that your processor is always executing one task. At all times on the timeline, it's going to execute one task. So the task that it's executing at any time is, among all the tasks, the one that has the highest priority that has not already completed its execution within its time window. Okay. By the way, the statement of this problem is non-trivial. The solution is actually pretty trivial, but the statement of the problem is non-trivial, and that's why these guys kind of got their names attached to this result, is that they came up with a clearly defined problem statement that turned out to be easy to solve. Okay? But the problem statement was the art of it, really. That was the major contribution, was just to find a problem statement that was easy to solve. Okay? All right. So the Liu and Leyland theorem is that among all the possible priority assignments you could give to these tasks, there's one that will always be at least as good as every other. Okay, in a very particular sense. All right, and the one that will be at least as good as any other will just give the tasks with the smallest period the highest priority. Okay, so the ones that have to execute most frequently have highest priority. Notice this is independent of their execution times. Execution times don't matter. That was another key breakthrough just by cleverly formulating the problem statement. They eliminated the problem of having to know the execution times, right? You just have to know how frequently the tasks need to execute, and you can assign them priorities, okay? Now, this is optimal in a very particular sense. It's optimal in the sense of feasibility, which means that if there is any priority assignment that will successfully execute all tasks within their time window, if any such assignment exists, then this assignment works. Okay? That's what it means to be optimal in the sense of feasibility. If any assignment can meet the deadlines, these are the deadlines, okay? The task has to execute by the end of its time window. If any priority assignment is able to meet those deadlines, then this priority assignment will be able to meet those deadlines. Okay? The hardest thing here is just getting your head around exactly what problem is being solved. And by the way, you know, many people who use this theorem don't actually understand the theorem because they don't understand what it's not saying, right? So it's common for people to just say, all right, I should just give highest priority to the things that execute most often. Sorry, but this theorem doesn't tell you that that's good. Okay? Stated that way, by itself, this theorem does not tell you much at all. Okay? You have to have all these other conditions. No precedence constraints, no mutexes, no interaction between these tasks. Okay? All right, so let's have a look at this. So I can walk you through the proof turns out to be, in general, to be a little bit tedious, although it's conceptually very easy. But it's very easy to show for 2 tasks, and the way that you show it for multiple tasks is very similar. It just involves a lot more bookkeeping. Is there a question? Okay. All right, so suppose you've got 2 tasks, and so the way we characterize these tasks is that they have a period, so that's the T, the capital T's. So this red task has a shorter period than the blue task. Now the execution times, those are these C1s. We don't need to know those execution times to assign priorities. That's a key in this result. You don't need to know the execution time to assign priorities. But you do need to know the execution time to know whether the assignment worked, whether it actually was successful in meeting the deadlines. Okay? So is the distinction clear? Okay. So we can completely ignore execution times for assigning priorities. So ignoring execution times, which of these 2 tasks should have higher priority? Yeah, number 2, right? The red task should have higher priority simply because it is executing more often. Now we're assuming there's no interaction between these tasks. We're assuming preemptive scheduling, okay? So let's look at this question of preemptive. What if we say, all right, we can't do preemption. It's going to be non-preemptive. Then, given these 2 tasks, is there any feasible schedule? Sorry? Assuming non-preemptive, is there any strategy here that can meet the deadlines for these 2 tasks? Not with 1 CPU, right? Obviously, right? The blue task takes more than 1 complete cycle of the red task, so anytime you decide to execute the blue task, you're screwed. You're going to miss deadlines on the red task, right? So with this particular formulation, there's no feasible non-preemptive schedule. So the only way you're going to get a feasible schedule is if you do preemptions, okay? So what will preemptive scheduling look like? Well, if suppose we give higher priority to the red task, then it could look something like this, okay? At the beginning of time, we begin executing the red task, okay? The blue task is, in a sense, preempted. It's not allowed to execute until the red task is finished, okay? When the red task is finished, we can now safely execute the blue task, but the next time that the red task becomes enabled, it's becoming enabled at a strict period. Notice, I mean, by the way, this is why people mess up applying this theorem. Notice that I'm not allowed to do the next execution of this early. Okay? That's a subtlety in this theorem, but it's necessary for the optimality. Okay? The task does not become enabled until the period has expired, and then it becomes enabled again. Okay? So it would not have been kosher to just, execute a bunch of reds first and then allow the blue to execute. If that is allowed, then is there a feasible non-preemptive schedule? Yes. Right? Because I could just execute the red a bunch of times, enough times to get ahead of the game, then execute the blue, okay, and then come back and execute a bunch of reds. Right? But in Liu and Leyland's formulation, that's not allowed. So as soon as the red becomes enabled again, at this point now there are 2 tasks that are able to execute, And under preemptive scheduling, at all times, the processor is executing the task with the highest priority. You're Chris. Right. I called Raphael Chris earlier, and you guys don't look at all alike. Okay. So has everybody got this? I mean, I hate to belabor it, but it's just so common to misapply this theorem that, yeah, question?
I'm a little confused about what period means. Is it just a time window in which a task should happen?
Yes. So the period specifically means a time interval over which the task should execute to completion once.
So, I mean, if you have another period of TI,
Mhm.
you have to then execute at the end of this period and again at the beginning of the
Yes, that's right. So you could get adjacent executions of the red. That's right. But it has to complete before the end, and it has to complete before the end of the next one. Okay? Yeah.
So in this structure, if we actually move the red one to the end of its period, start the red one again at the beginning of the next period, when we actually running this code long?
Very, very good observation. So the observation is that, gee, it was kind of silly to execute the red at this point, because we're going to pay an overhead for context switching. By the way, this model here assumes context switching is free, but it isn't, right? How do you do context switching? Well, you copy your machine state into a thread data structure, which is going to take several cycles, at least as many as you've got registers, okay? And then you're going to have to restore that state eventually again. So it costs many cycles to do this context switch. And this particular context switch was a stupid one to do, because I could easily have met the deadline by just letting blue complete and then executing the red. And there would even be some headroom there, right? Because the blue would actually, if I let it complete, it's going to complete at this time. And then the red will execute right after that. So there's nothing about this theorem that says that this schedule is optimal in any sense other than feasibility and under the assumptions that context switching is free and so on. Yes, that's right. So one problem is you would have to have confidence that the blue is actually going to finish early enough to allow the red to execute in order to be able to apply that optimization. And as I said, worst case execution time is a fiction. So how can you have that confidence? Okay. All right. So Liu and Leyland, once they had very carefully formulated the question, yeah, oh yeah. Yeah, who decides the period? That's another good question. So again, just like a lot of these, when we talked about assigning priorities, most of it was, kind of very heuristic. It was something that sort of made intuitive sense or seemed to fit the problem or something like that. That's often the case with periods too. You're doing a control algorithm for a robot, and you decide to run a task at 100 hertz, right? Every 10 milliseconds. Why? I don't know. Seems to work. Now, sometimes you can use more principled things, like you can use the Nyquist-Shannon sampling theorem. If you're dealing with discrete time samples of data, then it gives you a bound on the period. But that's often actually a loose bound anyway, because you don't really know what the bandwidth of signals is. And you can always sample at higher rates, and there's often advantages to sampling at higher rates. So there's a lot of design that goes into figuring out what periods to assign to tasks. All right, so here's so the first thing that Liu and Leyland observed, which is really what makes it easy to prove that this strategy is optimal with respect to feasibility, is that they said, well, the major complication is that you've got these periodic tasks, but how they align relative to one another, there's lots of possibilities, and that alignment affects the overall behavior of the system. So the simple observation that they made was that things are never worse than when all of your tasks become enabled at the same time. Okay, that's the worst possible scenario. And what they meant by worst possible scenario is simply they looked at the completion times of all the tasks, and they said that you might, if your tasks do not align, do not all become enabled at the same time, you might complete early, but you will never complete later than if all of your tasks become enabled at the same time. That's the worst possible completion time can be determined for all the tasks just by assuming all tasks become enabled at the same time. Okay? So this picture is meant to support that hypothesis. This first scenario is where the blue and the red task become enabled at the same time, and the blue task completed at this point. If the red task had become enabled earlier, then the blue task would actually finish earlier, but it would not finish later. If the red task had become enabled much earlier, the blue task would finish even earlier, okay, but again, not later. And here, you know, still earlier, well, now the blue task finishes at the same time, but again, still not later. Okay, so this is actually kind of easy to prove geometrically for these two tasks. You just do this sliding window kind of thing, and it's easy to see that the worst scenario is when the two of them start at the same time. Now, in the Liu and Leyland paper, the bookkeeping to show this for an arbitrary number of tasks is tedious, okay, but the concept is exactly the same. All right, so it's enough to look at the situation where all the tasks start at the same time. Then, once you consider that situation, to look at optimality with respect to feasibility, you only need to check two things. One is, if you choose a non-RMS schedule, non-rate monotonic schedule, and you get something feasible, then does that imply that the rate monotonic schedule will also be feasible? Okay? If you can prove that, then you've proven that the rate monotonic schedule is optimal with respect to feasibility. Okay? So the non-rate monotonic schedule says execute the blue task first, because that's not the rate monotonic schedule, because the blue task has the bigger period, right? So the rate monotonic schedule said you want to give higher priority to the red task. The non-rate monotonic schedule says, let's do the wrong thing here, right? And execute the blue task first. Now, under what conditions will that schedule be feasible? Yeah.
C1 plus C2 is less than T2?
Right. You just need for the execution time of the blue plus the execution time of the red should be less than T2. And if that is true, then the poor choice of schedule is feasible. Okay? So this condition. As long as this condition is satisfied, the bad choice of priority assignment works. It does deliver a feasible schedule. So now all we have to do is show that if this condition is satisfied, that the rate monotonic schedule is also feasible. Okay? And then we've shown optimality with respect to feasibility. Right? So is it? Well, yeah. If C1 plus C2 is less than T2, then giving the red task high priority also leads to a feasible schedule. Okay? So does everyone get the idea of the proof technique here? It's actually pretty clever proof technique, and tedious again when you extend it to multiple tasks, but the concept is exactly the same when you extend it to multiple tasks. All you have to do is you say, well, if any poor priority assignment gives you a feasible schedule, then the good priority assignment will also give you a feasible schedule. Notice this says nothing about what happens if the schedule isn't feasible. Right? If there is no feasible schedule, there's no reason to believe rate monotonic is any better than anything else. Okay? All right. That's about it for rate monotonic. So this is probably a good time for let's take a 2-minute break, and then we'll look at variants of earliest deadline first, which are more dynamic and actually a lot more interesting.
Next Thursday, so like, is there some other way for me to take the midterm? Like, since I'm not, I guess I'm on the class, I just like take it home and do it and like.
Yeah, that would be fine. Or alternatively, I'm actually going to be administering it early to 2 people in the class, so you could take it early.
Is it on like Tuesday or Wednesday?
It's both. I don't remember the times, but if you send me email, I can send you the details.
Okay, that works actually.
Okay. Remind me your name?
Diana?
Diana.
With a G.
Guyana. Oh, okay.
So you mentioned last time that if we want to use the Husky or some expensive form of equipment, then we should mention it to you.
Is this your team?
Yes.
Okay. Right. I don't have any visibility into whether other teams are also planning this right now is the problem. I would suggest you put this on the spreadsheet that Di indicated, okay? And let's see, we'll figure out a way to resolve it.
Okay, good.
All right. Okay, let's get started now. I just wanted to mention briefly one practical issue with rate monotonic scheduling, which is how do you implement it? And so one of the key things, of course, is that when do you make scheduling decisions? Well, here the assumption is there's no I/O, one of the hopelessly unrealistic aspects of this, right? But so it's not like there's going to be externally triggered interrupts that are going to trigger your scheduling decisions. So when did scheduling decisions get made here? All right? Start of every time period, right? Anytime a task becomes enabled, okay, that could change what you want to execute. And only when a task becomes enabled for its next execution would you want to change, right? So what you want to do is, given a bunch of TIs, the periods, whatever they are, you want interrupts to occur at all of the multiples of those periods, right? So one way to set that up would be to have a separate timer interrupt for each of your tasks that you initialize, and then it triggers at that period. You might not have enough timers to do that on the hardware. That would require separate timers, yeah.
Doesn't the scheduler actually come every time when we have a task finished, so we switch to another task? That the scheduler actually switches the timers instead of the whole.
right?
But I mean, when each task like switches, is the time that when we actually say, oh, this is.
Yeah, that's a good point. So when a task finishes, you'll want to resume a task, right? But interestingly, unless some other task's time period has kicked in that intervening interval, then you'll always be resuming the task that you preempted here. Okay? So that makes the scheduling decision relatively easy if you haven't gotten one of these timer interrupts in here. Right? Okay. So let's see. There's no eraser. I'll just use the other board over here. All right, so I'm executing some task, and it's got, say, if it were executing open loop, this would be its interval. Another task preempts it, okay, during this period. So I now have a hole in this execution, and the execution time of this task is going to extend out, right? Now the question is, what is the scheduling decision to be made at the conclusion of this second task? Okay? If these are the only two tasks, then obviously the only thing to do is to resume here, right? If you have a third task somewhere, then unless that task became enabled in this time window, all right, then prior to this time window, this task had higher priority than this task, right? So unless the task becomes enabled in this time window, the correct decision is still to just resume where I left off, right? So yes, so but you're right that in a sense there is a scheduling decision to return to that task, but it's an easier scheduling decision. The time when you need to make interesting scheduling decisions is when those interrupts occur and a task becomes enabled. And at that point, you have to choose the highest priority enabled task, okay? And actually, it may be a simpler implementation to also just make that decision, the same decision at this point, right? So if an interrupt occurs during this interval such that one of the other tasks becomes enabled, then you just record that in a data structure, and then when this resumes, you just look for the highest priority task that is enabled. So that's probably the simplest implementation anyway. Yeah. Okay, but in any case, you don't need interrupts for these, right? When these tasks execute, when these tasks terminate, that's going to be some thread procedure returning, right? And it returns to a known location. You have some code to execute there. So that can be your thread scheduler. So what you do have to do is provide these timer interrupts to handle the periodic invocations of the tasks. If you don't have enough timers to have one per task, then your only choice is to have timer interrupts at the greatest common divisor of the periods. So this suggests that if you pick very awkward periods, if you have one task running at 100 hertz and another task running at 101 hertz, okay, then how often do your interrupts need to occur if you only have one timer interrupt? So task at 100 hertz and 101 hertz. All right, so this is 10 milliseconds is the period, T1. T2 is rather awkward number. Something less than 10 milliseconds, right? 9 point something milliseconds. Okay? How often do you need to, how often will you need your timer interrupt to occur? This would be a good question for the second midterm, since it isn't in scope for the first. Well, yeah, on the last week, we're doing a second midterm rather than a final so that you can focus on your projects after classes end. So Greatest common divisor of the periods, which is what? So you could look at the least common multiple of the frequencies. All right, so what's the least common multiple of these two frequencies? 10,100 hertz. Okay, so this would be a pretty unfortunate choice, right? This means that in every 10 millisecond execution, you're going to get approximately 100 interrupts. Most of which are not going to have anything interesting to do. Right? So you kind of need to pay attention to these issues. It can get even worse, of course, if these frequencies are determined by external hardware, right? Then they could, in fact, not even be rational multiples. Right? So anyway, these are issues. All right, so let's look at deadline-driven algorithms. So there's a whole bunch of these, but these are actually quite a bit more flexible. They do eventually allow precedences, and with some cleverness, they can deal with mutual exclusion protocols. There's a whole string of work from the scheduling literature, several PhD theses on this, several well-known failures due to poor choices of scheduling algorithms, including, I'll talk in some detail about the Mars lander, the rover lander, which had problems due to its scheduling algorithm. But the first formulation is relatively straightforward. It's called Jackson's algorithm, and it dates back to 1955. And it says if you've got n independent one-time tasks. By the way, this was done in the context of operations research, not software scheduling. Okay? There's a lot of job shop scheduling literature where operations research people were focused on, how to get the most use out of factory workers and factory machinery. And so they looked at a lot of these scheduling problems and developed a lot of the original scheduling theory. So you have a set of one-time tasks, and you've got some deadlines. Then if you want to schedule them to minimize the maximum lateness, so the maximum lateness is defined as the difference between the time you actually finish task I and the deadline. Okay, so that you finish at a certain time, and so the lateness is negative when you finish early, and the lateness is positive when you finish late. Seems reasonable, right? So if you want to minimize the maximum lateness, then you can use this earliest due date algorithm, which is simply to execute them in the order of non-decreasing deadlines. Okay? So this is the scheduling policy that I use mostly for just about everything. Okay, if it's due tomorrow, it has the highest priority. If it's due next week, it has lower priority. It doesn't matter how long it takes. Right? Notice that this is also independent of execution times. Yeah.
How does this differ from the rate monitoring schedule?
Yeah, so the question is, how is this different from rate monotonic scheduling? So that's an interesting question. Someone want to comment about that? This is, by the way, actually, this is the hardest part about these kinds of algorithms, is really understanding the nuances about when one applies and when one doesn't. But yeah.
Isn't the rate schedule looked at how big the task itself is, not the period? This is looking at.
Well, no, not really. Both strategies are ignoring execution times in assigning the strategy. This one doesn't pay any attention to execution time, neither does rate monotonic scheduling in assigning the strategy. Now, the execution time affects feasibility, and here it'll affect lateness, right? But it won't affect whether your strategy minimizes the lateness. This strategy will minimize lateness irrespective of execution times, right? So that's not the difference. What is the difference? Why can't you just treat the end of your period as a deadline and apply this algorithm? A very good question. Yeah.
Is it because it's a one-time task?
That's a big part of it. But there's kind of a bigger issue, which is that this assumes not only that these are one-time tasks, but you know what they all are right at the beginning. And they're all enabled immediately. Okay? In rate monotonic scheduling, they're not enabled immediately. They're enabled to execute when the next cycle starts. Now, when you first start up the system, you might align all of the periods, okay? But they very quickly get misaligned. So you might be able to use this to get the optimal schedule for the very first execution of every task, okay? But it won't work to give you the optimal execution for subsequent executions because you don't have this scenario. Moreover, and by the way, that's the reason why, the rate monotonic scheduling result does not minimize maximum latency. Maximum lateness. There's no theorem, and it doesn't, in fact. You can find counterexamples that show that rate monotonic does not minimize maximum lateness. Okay? So this is actually a stronger theorem than rate monotonic. This is a stronger optimality constraint. Minimizing maximum lateness certainly implies being optimal with respect to feasibility, right? Any schedule that minimizes maximum lateness, if there's any schedule that's feasible, that one's going to be feasible, okay? But it's a stronger result to minimize maximum lateness than to just deliver a feasible schedule, okay? It's very subtle distinctions, but the problem formulations are really the art here, is in how you formulate the problem, okay? All right. Another thing to notice is that this does not require preemption. It achieves a stronger form of optimality without any preemption. Okay. So it's relatively easy to prove. You can use an interchange argument. The intuition is simply that if you're given a schedule that is not earliest date or earliest due date, then somewhere in that schedule there must be tasks A and B where A immediately precedes B in the schedule, but the due date of A is greater than the due date of B. Why? Why must that be true? Right, because otherwise it would actually be earliest due date. If there's no such pair of tasks, then we have an earliest due date schedule. Okay? So if we have such a pair of tasks, then the proof technique says, well, just swap them, and your schedule is better. You can show that the lateness is reduced. Okay? And that argument is enough to show that among all the schedules, all of the priority assignments, the earliest due date is the optimum one in the sense of minimizing lateness. So that proof is kind of written out in gory detail here, but I'm not going to walk you through it because you can just look on the PowerPoint slide and look at it. But the real art here is in the problem formulation and the problem statement and knowing when to apply one of these theorems, because the differences between them can be extremely subtle. So let me give you a couple more variants, right? So earliest due date doesn't allow tasks to arrive. Okay, that's one of the differences that it has with rate monotonic, which does allow tasks to arrive. In rate monotonic, the tasks are arriving periodically, but they are arriving. Okay, so earliest deadline first says, given a set of n independent tasks with arbitrary arrival times, any algorithm that at any instant executes the task with the earliest absolute deadline among all arrived tasks is optimal with respect to minimizing the maximum lateness. So here's a question for you, and I'll let you puzzle over this before next time. what's the difference between this and rate monotonic? It allows arrivals now, and it's asserting a stronger optimality result, which is that it minimizes maximum lateness. Okay? And if you can get clear in your head what's the difference between this and rate monotonic, then you've basically nailed most of scheduling theory. I mean, seriously, if you can get those distinctions clear, then all of these variants of scheduling algorithms become easy. All right? So I'll let you think about that before next time.